All right, let's get started. Hi, my name is Fagrell.
Hi, Per.
Hello. And this is how to write actually object-oriented Python. Before I really dive into this, I just want to say I have a handouts version of this, so you don't have to break your wrists trying to type everything out. I've got a couple of paper copies, and it'll be available afterwards as a PDF. So I'm going to start today with just enough about me to make you trust me. Sort of explain the difference between object orientation and regular procedural programming. And then the bulk of the talk is going to be 6 design principles to help you write object-oriented code. Finish with some parting thoughts, and hopefully there'll be time for some questions at the end. So as I said, my name is Per Fagrell. I come from Sweden. I live in Stockholm right now. And I work at Spotify as a backend engineer. I've been using Python for the last 6 years, and I love it. But before that, I've used a number of different languages in my professional career, and as relates to this, I've done object-oriented design in all of these languages. So I've seen it from a bunch of different angles and a lot of different environments. So let's dive into the actual information here. Procedural versus object-oriented programming. What is the difference? So procedural programming is basically your old school recipe style programs. It's your hello world. It's what you're writing your scripts in. You do everything step by step. It's pretty easy to wrap your head around. And there's always this like clear thread of control going through your program that you can just follow along. Oh, really? And I figured this might happen. If you give me a second, I'll just switch to the PDF version. Oh. All right, where were we? All right, the duck. Great, so there's this easy thread of control that you just follow along through, which makes it really simple to grasp. And it's made to be simple because it's the only thing computers really understand. So object orientation is very different. Because first of all, you're not even using objects. You're writing classes. So basically you're working with blueprints and interaction descriptions, not the actual thing that gets loaded into memory. And then once it is in memory, it looks more like this. It's a group of people whispering in each other's ears, introducing each other to their friends. That's sort of the high-level view of objects and message passing. And that's a bit harder to wrap your head around when you're getting started than just plain procedural programming. So people coming into object orientation do tend to sort of just do what they have been doing, but with a couple of objects thrown in. So if this is so much more complicated, why do we use object orientation at all? Well, object orientation maps your mental model to code better than any other paradigm we have right now. So the words and the concepts that you talk about your problem with are the words and concepts in your code. And there's a direct map there. So it's much easier to think about what's going on in your code. All right. Python as a language gives you a lot of freedom when it comes to what paradigm you want to use. You can write everything from one-off scripts and little frameworks and server applications up to really big desktop applications completely with procedural code or completely with object-oriented. There's nothing holding you back from doing that. There's also nothing stopping you from shooting yourself in the foot and putting these in a blender and just hitting puree, or dropping entire programs into your methods. So there's nothing in Python that forces you to be consistent to one of the styles. And to get that consistency, you have to apply some discipline on your own. Is it worth that extra energy? I maintain that, yes, it is worth it. And I hope to show that consistency to object orientation will improve the maintainability of your code, that it simplifies the testing of your code, and above all, that it simplifies communication with your future self when you come back to it and anyone else working on that code. So now for the bulk of this talk, the design principles. All right, so Some of these are worded like they're talking just about classes. All of these concepts apply at pretty much any level, from the functions and methods, classes, modules, up to the program level. So just sort of keep that in mind. So the first 5 principles are called the solid principles. They were sort of brought together by Uncle Bob Martin. And these are sort of the basis of object-oriented design. The first one is the single responsibility principle. It says code should have one and only one reason to change. That's a really narrow definition of responsibility. When we talk about responsibility in our day-to-day lives, it's usually a much broader concept. If someone says, hey, Perry, you're in charge of phones, that responsibility means I'm going to be taking calls, making calls, doing all the talking. I won't be doing any handovers there. If you take that thinking and apply it straight into your code, you end up with these large classes like this, where you have one modem class and it's doing the dial-up to the server, and any handshaking there, it's going to take care of all the sending and receiving data and so on. Well, what's the problem with that? First of all, we have a big class, a lot of code. The larger the risk of actually breaking something when you go in there and try to update it or fix something. Your test suite is going to be a lot larger. So finding the relevant tests for what you're doing is going to be harder. And then you just simply have the fact that there are 2 reasons for this code to change. If the handshaking with the server needs to be updated anyway, you have to come in here and make a change. If the way you are sending and receiving data needs to change, you have to come in here. So you have the fact that if you're several people on a project, you might just be stepping on each other's toes. The risk is increased of simple screw-ups there. So the obvious and easy way to fix this is to find those single responsibilities and break the class apart along those lines. So now we have a connection manager, and all it's doing is the handshaking and the teardown with the server. And you have a data transceiver. Now all it's taking care of is getting the data back and forth. So we've taken this big object and we've broken it into 2 smaller ones that are easier to test and to see what's going on in them. And if we want to have that runtime modem object to use, we can simply wrap them in a new object called modem still. But then its single responsibility will be delegating to those classes that we had earlier. So it's only doing one thing. Another common thing is when you have objects which are taking care of some business rules. Here we're calculating how much we're going to pay this guy, but we're also doing persistence in this object. So when we want to change how we calculate what we're paying people, we have to come in here and make changes. But also if we want to stop writing things to file and start using databases, then we also have to come in here. And the same problem with the tests and so on. So the obvious choice here is to break out persistence. Say, here's my guy, save him to whatever backend you're using right now. Or, since this is Python and it's easy to do, you can create a mix-in class. So at runtime, you can still take your object and say .save, and it does that. But as far as maintaining the code and testing the code, you've split it in the code base, so it's easier to work with. One last example here. You have this block of code which is doing some orchestration. We have this input processor, this output processor, and we're telling them what to do. But then we're doing this calculation of our own in the middle. So there's a number of things that could sort of screw this up. First of all, if you have to change how you're interacting with the other objects, that makes this code have to change. But also if the algorithm you're implementing in between them changes, you have to go in here and make changes. And testing this is more difficult because now you're probably going to end up with a lot of tests set up where these objects that you are interacting with, they have to be mocked out and then set up precisely to sort of poke and drive that code that would have otherwise been really easy to test all on its own. So if we break that code out, and now all we're doing is orchestration. This code becomes much simpler because all it's doing is tying these things together. And testing that block of code is simpler because it's off on its own somewhere. you don't have to set up a bunch of other objects to test it. And here we see that. So that is the single responsibility principle. I spend a lot of time on it because it's one of the really big ones. If you only apply this principle, you're still going to come a really far way with it. Right? So the O in solid is the open-closed principle. This one's a bit more strange. So code should be open to extension, but closed to modification. So you should be able to add new behavior by writing new code, creating new classes, fun stuff. But to make that code work, you shouldn't have to go back and modify the old code. It should work as is. So basically, if you give new tools and ideas to a master craftsman, he's going to be able to work with that interchangeably. He doesn't have to change anything about who he is. And the same thing should apply to your code. So I have this function here to validate a list of links. I have text links, and I'm creating an object of that link. These are links to a music track. I don't know if you guys are familiar with Spotify URIs. They look like this: Spotify :track : and there's a hash. This is how you identify a song. So I'm creating this track object, and I'm validating it. But now I want to extend my program with new behavior. I want to support links to albums, right? So I write this album class, which is great. But for that to work with this code, I now have to come in here and change it somehow. I have to add support for that. So the not good way, so to speak, is to do something like this, where we're doing an if-else to create whichever one is right for this particular object we're going through. Well, we're basically violating single responsibility principle here. If we add new classes, I have to change this code. If I change how I do validation, I have to change this code. We're doing too much at once. So the obvious thing to do here is to break out the responsibility of how do I create these link objects into something separate. Now I have a URI factory making these. I don't have to ever come back into this code, no matter how many new and different use cases I add, no matter how many new of these classes I write. This just works. Can you know up front that your code will work like this? Sometimes. Mileage will help. Just having written a lot of code and seeing this is going to be something I have to change. But otherwise, the open-close principle is the one with the most gray zone, right? So you're probably going to start with the simple solution. You're going to add some classes and say, oh, I have to go back and change this every single time. And then you'll refactor. Here's another example where we're loading settings from files on the hard drive. And if I want to extend this by adding a new file, a new loader, I have to come back and rewrite this function because I'm explicitly listing all of the things I'm loading. I can break out all the knowledge about which function goes with which file. So that's purely a configuration thing. Now this load function is completely agnostic to the code around it. I can add more and more loaders without having to rewrite this function. And testing it is dead simple because all I have to do is run the load function and see, is it actually picking up my configuration? So that's the open-close principle, just writing code so that it doesn't have to be rewritten again and again. All right, the L in solid, with the most imposing name of them all. The Liskau substitutability principle, big name, very simple concept. It's basically duck typing. Anywhere you use a base class, you should be able to use a subclass and not know it. So it's enhanced duck typing, really. No matter how bizarre a subclass you invent, or object in general, because this is Python, you don't have to use inheritance, it still needs to behave like that original object you may be replacing. So not only do you need the same interface, the same methods, you also want the same behavior. If the original object doesn't require you to do things in a certain order, your subclass shouldn't suddenly require that as well. Or rather, let me rephrase that. The subclass shouldn't suddenly require you to do things in a certain order, unless that was already there in the base class. Because otherwise what happens is people have this code that was working, you write something new, and it breaks. And then people are going to do if is instance subclass, and now you're violating the open-close principle, because for every other subclass, you're going to go in and write a new one of those. And that's a terrible idea. So that's the Liskau substitutability principle. Understand and value the power of duck typing. Almost through with the solid principles here. We're on to I in solid. So the interface segregation principle. This is an interesting one. Don't force clients to use interfaces they don't need. What? Okay. So if this was, for example, a C++ or a Java conference, this would be really easy to talk about. We'd have an interface or an abstract class for input-output streaming. And we'd be talking about how easy this is for our file, which we're reading and writing to, and it's great for our database, which we're reading and writing from. And then someone comes along with a line printer, for whatever reason, and writing makes a lot of sense, reading doesn't, and they raise not implemented exception or something like that. Suddenly you have all this code that used to work that's getting stack traces. And say, how do we fix this? Well, we'll split the interfaces into the smallest components that make sense. Now, if you only support writing, you only implement, one of these and not the other, and you get some help from the static typing. All right. How does that apply in Python? Well, fortunately, we have duck typing to help us a little bit with this. So as someone who is writing objects that are being passed around, duck typing saves the day, because if a method isn't being used, you don't have to write it. It doesn't have to be there. So we don't have to write small interface descriptions like that. When you're using objects, however, you still need to consider how much of this interface am I using? How many different parts of the objects I'm given am I using at a given time? Because the more you're using of different modules and different objects, the more tightly coupled you are to it. And after a while, you can end up being sort of ensnared in it. And if it's a third-party module, then your code may be breaking the next time they push a new release. And if they're dependent on you, then they're kind of stuck with whatever it is you're forcing them to write. So it's just something to be aware of. And that's the interface segregation principle. So the last one, the last solid principle here is the dependency inversion principle. This one is my favorite. It says high-level modules shouldn't rely on low-level modules. Both should rely on abstractions. Again, C++ and Java, you have the interface, you have the virtual classes. This is Python, so abstractions are literally abstract. There's nothing there. So this is so abstract, I need a concrete example here. I'm writing a music player. Something I like here. So I have this music player object, and it's keeping track of my playlist, lets me step through the songs, start playing music, stop playing music. Works sort of the way I want it to. And then we look at how I'm implementing these. Well, to play music, I'm going to need to open the song on my hard drive and read it in and give it to the sound system so that it knows what to do. And, well, I'm going to immediately run into some problems here, right? So when I start testing this, I realize that, all right, there's a lot of file I/O. There's an entire audio subsystem. This is going to be a lot of mocking or living with the speakers turned off every time I run the test suite. That's terrible. And then I realize, playing sound locally, that's boring. I want to stream it over the internet. Streaming music, that is the future. So what's going on here? I have this object which is doing state of playback from a playlist is one of the things that it's doing. I mean, and that's a high level abstraction. This is on the level I can explain to my mother what it's doing. It's also doing some file I/O and dealing with an audio subsystem. This is bare metal computer science almost. So I have this mixed abstractions. And in a sense, it's kind of like a single responsibility principle coming back again, where we shouldn't be mixing these two different areas. So if I take this music player that I have, and I break out all of that stuff, so now I have this audio player which knows about the files and the audio subsystem. Testing it is now a lot easier because I could just send in a stub that says, you know, keep track of how you're used, but don't do anything. Now testing is a lot faster, and I don't need to turn off my speakers every time I run the suite. And again, if I decide that, hey, locally, that's boring. Streaming, that's awesome. Now I just implement the code for streaming over the network as another object here. And I even get the advantage that I can swap them at runtime if I want to. So that's the dependency inversion principle, which is basically keeping your abstraction levels separated like that. And those are the 5 major object-oriented design principles, the solid principles. There's one more for today, which I think is sort of also very important, a little bit more intermediate level here. So tell, don't ask. Tell objects to do the work you want done. Don't ask them for their data. This one is really important. I mean, basically, if you have a butcher that makes great sausages, you tell him to make you some sausages. You don't ask for casings and pork. It makes sense there, but we tend to do this in code all the time because it's so easy. You're doing some calculation, and you need the cost of a bill. And you're like, all right, this is like 2 lines. I'll just go through all the items and add them up. Now we have suddenly code relating to this bill spread throughout the system in a couple of different places. Not necessarily tested at all or well in all of them, and possibly broken in at least one. Empirical measurements say it's definitely broken in at least one. So instead of asking this object for its data and doing the calculation, we should tell it that we need the total cost. We now have all this code collected in one place, which is sort of the point of objects. We only have to test it once, which is great. And this object might actually know a bunch of stuff that we hadn't thought of. A bill object may know about sales tax, or gratuity, or tips, which we had forgotten to include in at least one place that we were using this code before. And this is especially important to drive home, in my opinion, in the Python community, because we have these awesome data types that are so easy to use. We have our tuples and our dictionaries and our lists, and it's really simple to just pass around data. And then you're doing all these calculations in all the different places that you're using it. But if you bring that into an object, you have one place to do all the testing, and you have much less code spread throughout your system. So that's the tell, don't ask principle. And that was actually all of the design principles, and I hope that you've seen that they are good. So my parting thoughts for this. Writing really good object-oriented code comes down to learning to think in objects. Anytime you're writing your code and you're having problems with it, there's a lot of setup for your tests, or you have this method which is taking like 18 arguments, or you're looping it over objects and taking all their data. You know, stop and say, am I missing an object? Oh, really? Oh, my bad.